Welcome, and thank you for joining this presentation on the Physicist's Toolkit. We'll explore essential concepts, methods, and tools that are fundamental to problem-solving in physics. Whether you're new to the subject or looking to refresh your understanding, this will provide a clear and practical overview to help you approach physics with more confidence and insight. Let's get started. To measure anything accurately, scientists agree on 7 fundamental units known as the SI base units. These cover all physical quantities and serve as the foundation for all measurements. They include the kilogram for mass, the meter for length, and the second for time. For electrical current, the unit is the ampere. Thermodynamic temperature is measured in Kelvin, the amount of substance in mole, and luminous intensity in candela. These units form a universal language that helps ensure we are all consistent when measuring the physical world. Derived units come from combining our fundamental base units by multiplying or dividing them. For example, speed is measured in meters per second, which translates to meters multiplied by seconds to the power of -1. Density combines kilograms and meters to the power of -3, reflecting mass per unit volume. Momentum is the product of mass and speed, so its units are kilograms times meters per second. Force, measured in newtons, combines mass, length, and time units as kilograms times meters per second squared. These combinations help us express different physical quantities using the basic units we already understand. Dimensional analysis is a way to check that an equation makes sense by comparing the units on both sides. Each physical quantity, like velocity or force, has specific units and dimensions, like meters per second for velocity or kilograms meters per second squared for force. When you write an equation, the units on one side have to match the units on the other side exactly. If they don't, it's like trying to fit gears that don't line up. The equation won't work and is considered invalid. This helps us avoid mistakes and ensures that our calculations are physically meaningful. Let's take a closer look at the dimensional formulas for kinetic and potential energy. For kinetic energy, which is 1/2 times mass times velocity squared, the mass has the dimension of m, and velocity, being distance over time, has the dimension lt⁻⁻1. Squaring velocity gives us L squared t⁻⁻2, so when we multiply by mass, the overall dimension becomes mL squared t⁻⁻2. Moving on to potential energy, which is mass times gravitational acceleration times height, mass is again m, gravitational acceleration has dimensions of lt⁻⁻2, and height is a length, L. Multiplying these together yields the same dimension, mL squared t⁻⁻2. This shows that both forms of energy have consistent dimensional units, confirming the dimensional correctness of these energy expressions. We'll now look at the laws of homogeneity, which are important rules to follow when working with dimensions in equations. First, any terms that are added or subtracted in an expression must have exactly the same dimensions. For example, adding 2 lengths together is valid, but adding a length to a mass over time is not. Second, the inputs for standard mathematical functions, like trigonometric functions, logarithms, or exponentials, must be dimensionless. This means you can't use values with physical units as arguments for these functions. These rules help ensure that the equations we work with are consistent and physically meaningful. Here, we see how metric prefixes help us move smoothly between extremely small and extremely large scales by using powers of 10. Starting from the base unit, we can go down to pico, nano, micro, and milli for very small measurements, which are all factors of 10 smaller with each step. On the other side, we have kilo, mega, giga, and tera to represent increasingly larger quantities. This system makes it easier to understand and compare sizes that vary greatly, from the tiniest particles to vast cosmic distances, all while keeping a clear and consistent scale. This slide reminds us that in physics, it's important to recognize the limitations of our measurements and the imperfect nature of the universe. The two targets illustrate different scenarios. One shows measurements that are close to the true value but scattered, indicating accuracy with high uncertainty, while the other shows tightly grouped measurements that are far from the true value, representing precision with low uncertainty but low accuracy. This highlights why physicists must always quantify how much doubt there is in their results, balancing both accuracy and precision to better understand what the data is really telling us. Now that we've looked at dimensional analysis, let's move on to understanding uncertainty in measurements. There are two key types to consider. Absolute uncertainty, which is the specific range of doubt around a measurement, like saying 11.1 meters plus or minus 0.3 meters, and percentage uncertainty, which compares that doubt to the actual measured value by expressing it as a percentage. This ratio helps put the uncertainty in context relative to the size of the measurement. It's also important to remember that the smallest division on the measuring instrument sets the baseline for this uncertainty and influences how many significant figures we report in our results. This ensures our measurements are both accurate and meaningful. Now, let's talk about how to handle uncertainties when you multiply or divide quantities. The key point is that the percentage uncertainty in your final result is found by adding the percentage uncertainties of each original value involved. So, instead of dealing with absolute uncertainties, you focus on their percentages and sum them up. This makes it easier to understand and calculate the overall uncertainty in your answer. Let's look at how to calculate the area of a room when the measurements have some uncertainty. First, multiply the length and width to get the raw area. 4.00 meters times 3.00 meters gives 12.0 square meters. Next, add the uncertainties in the measurements. 2% for the length plus 1% for the width equals a total uncertainty of 3%. Then, calculate what 3% of the area is, which comes out to 0.36 square meters. Finally, express the area with this uncertainty, rounding to match the precision of the instruments, so we write the area as 12.0 plus or minus 0.4 square meters. This method helps us understand not just the size of the room, but also the possible range due to measurement limits. Now, let's look at the difference between scalars and vectors. Scalars only have magnitude, which means they measure how much of something there is. Examples include time, mass, temperature, and energy. Vectors, on the other hand, have both magnitude and direction. This distinction is important because knowing just how much isn't always enough. We need to know which way as well. Things like displacement, velocity, and force are vectors. For instance, if you think about a dog moving forward, the vector shows the direction from its tail to its head along with how far it has moved, combining both size and direction into one measurement. Here, we are combining two movements, one going 11 kilometers north and the other going 11 kilometers east. By treating these as the two legs of a right triangle, we can find the straight line distance, or the resultant displacement, by applying the Pythagorean theorem. Squaring each leg length and adding them gives us 242, which, when we take the square root of, results in approximately 15.6 kilometers. This distance is the shortest path back to the starting point if you were to go directly, combining both the north and east movements into one. To add two vectors, first draw the first vector, A, to scale. Then, from the tip of vector A, draw the second vector, B, also to scale. The resulting vector, R, is drawn from the starting point of vector A to the end point of vector B. You can then measure the angle between the vectors and determine the length of vector R by the scale used, completing the vector addition graphically. Let's now connect everything and break down how we handle complex motion. When dealing with a force at an angle, we simplify it by resolving the diagonal vector into two parts, one along the horizontal axis and one along the vertical axis. We do this by using the angle theta to find the components. Multiplying the force by cosine of theta gives the horizontal component, and multiplying by sine of theta gives the vertical component. Once we have these, we can rebuild the original force using the Pythagorean theorem by taking the square root of the sum of the squares of these two components. This approach makes analyzing motion clearer and more manageable by fitting it into a straightforward grid system. Now you have everything you need to move forward confidently. This toolkit gives you clear units to measure your progress and dimensions to check and verify your understanding. It also includes a way to account for uncertainty, so you stay grounded in reality. Finally, it provides vectors to help you navigate through complex situations with direction and purpose. With this framework, guessing becomes a thing of the past, and you can approach challenges with clarity and precision.